Good afternoon. So we're continuing out order execution. If you remember last time, we talked about the three key things that you want to add in order to support out order execution. The first one was a mechanism for tracking instruction, which we haven't talked about yet. The other two that we talked about was a mechanism for recovery and a method to eliminate the unnecessary uh, hazards, which was write after write and write after read hazard. For recovery, what we proposed was the notion of retirement. And we said that we essentially, instead of writing everything permanently into the register file or to the PC or to the memory, we write it to this temporary storage unit called reorder buffer. And only when all the previous instruction reached to the reorder buffer and already retired, then we retire the instruction. So it's kind of like becomes a method like you have these instructions and this is your processor. So you read them in order. So the fetch and decode is in order. Then you will have a mechanism to kind of like shuffle them and run them in whatever order that you want. But then you will have this thing called reorder buffer that you make sure that things are back in order. And then you start basically retire them in order. So you retire the first one first, and then the second one, and third one, and so on and so forth. So you kind of like, read things, reshuffle them based on the availability that we're going to talk about in this lecture. And then you put them back in order and you let them go or retire them or commit them as some other people refer to this stage in order. Okay. The good thing about this is it allows you to recover the processor very efficiently. That if there is any mistakes and any instructions that they weren't supposed to be executed, all you need to do is basically discarding your ROB and then just redo the things in the correct format. And that makes the misprediction, any sort of speculation, fairly straightforward. We also talked about another important thing called renaming. So renaming was this strategy where we basically map what we call architectural registers. These are the registers that we use in the ISA, and map them into what we call physical registers. These are the actual registers that we have in the processor, which tends to be much more than the number of architectural registers, because architectural registers, you are basically limited to what ISA provides to you, which is usually, for example, in this ISA that we are looking at is only 32. But the physical registers depends on how much space and power and area we want to dedicate to our register file. So this kind of mechanism of mapping architecture to physical registers is called renaming. And renaming, as I said before, happens during the decode stage, allows you to kind of decouple this mapping, and then afterwards you can just deal with the physical registers. And then the benefit of this was it allows you to kind of eliminate the scenarios where you have unnecessary write after write. So for example, if I have things like add x5, x3, x2, and later on in some other instruction, I have something like sub x5, x4, x6. In out of order execution, since these are dependent to each other due to the output dependence, I cannot move this before this, right? So I'm limited by the order because the outputs are the same. If I do sub before add, I'm going to run into problems. But if I change these registers to new physical registers, so for example, call this P5 and call this P4 or whatever other names that we want to call them, then I can basically move this around as I wish because they're no longer dependent to each other. As I said, that doesn't necessarily mean that we can always fix this issue. First of all, it doesn't fix the raw data hazard issue. We still need to make sure that we maintain the dependency for read after writes. And also in terms of like how many registers are available in our free pool and all, we might have limitations. But in majority of time, given that the number of physical registers are significantly more than the number of architectural registers, this is possible, and this is what we use in order to improve the performance. Okay? So now with these two pieces of information that we learned, let's actually kind of complete the design and then give you a full example of an out of order execution, the steps. What you will learn today is that out of order execution, there are many different ways of implementing out of order execution. So unlike in order, which is kind of straightforward, out of order, there's a whole bunch of different ways of implementing things. In the rest of the lectures, we're actually going to go over some of those design decisions and going to give you a little bit of trade-offs between them. And then you're going to see how this also relates to your computer assignment 3. Okay? So just to recap the rerob and renaming, well, let's actually talk about the important part of the out of order execution, which is the scheduling. So we fetch and decode things, we rename things. Now we need to feed this into our pipeline in order to start executing things. And there we need to basically understand which instruction is dependent to other instructions and how do we actually correctly execute the instructions. So for example, let's look at this example here that I have I1, I2, I3, and I4. Let's say, for example, the first one is an add, the second one is a sub, the third one is an add, and the fourth one is also an add odd. Okay? So in order to be able to run these instructions, all we need to do is basically tracking which one is ready. What is the notion of readiness in our examples? There are two things that we need to check, right? We need to check whether the operands are ready. Okay. And this further means that there is no dependency. So no dependency. So what does that mean? Take a look at this example here, right? Take a look at, for example, X3 and X3 here, right? If I rename this, I'm going to, for example, rename this into, I don't know, like P3 or whatever. And if you remember, we're going to use the same physical register here, okay? For the source, we're not going to rename things, right? So what this means is that this instruction cannot happen before this instruction. Because if I do reorder these two instructions and run I3 before I1, I'm going to run into an issue which this value should get its updated value from here, but if I run it beforehand, then I'm not going to do that. I'm more than happy I can easily like move around like I2 or I4. I can move these things around because there is no dependency between the instructions, but I3 is dependent to I1, okay? So when I say I need to basically check whether my operands are ready or not, that's what I mean. So I look at P3 and I realize that P3 is dependent on the results of this I1 instruction. So I can only run I3 when I1 is finished, right? Is completed. So I need a mechanism to, first of all, understand these dependencies. And then an important thing is that I also need a mechanism to kind of wake up I3 or tell I3 that now your dependency has been resolved, you are good to go. So there are two mechanisms that we need to do. We need a mechanism for kind of selecting which of these instructions are not dependent. And then we also need a mechanism that we call waking up to kind of wake up I3 when I1 is completed. So I3 gonna basically stays in whatever scheduling queue that we have, waiting for I1 to finish. But when I1 is finished, we need to wake I3 up and say that, okay, here's the updated value. You can now go into the execution unit. Okay? So this is the main part of the scheduling queue and scheduling stage in our pipeline. Uh, and then this is essentially fix the raw data hazard problem as well. That if we can actually track the readiness, we will not allow instructions to be reordered if they are dependent to each other. And the waking up logic that we're going to talk about is going to take care of the forwarding. So once I1 is complete, I need to somehow forward the results back into I3, allowing the I3 to start being executed. So I need the forwarding logic basically to be implemented in this system as well. Okay? So how do we do that? We introduce this new component in our pipeline called reservation station, or RS. Reservation station sits right after the decode stage, and what it does is a table of multiple rows, and each instruction, each decoded instruction is written into this reservation station, and you kind of track the readiness of each of the components within this. And then this will be the kind of division between the in order part of the processor, the quote unquote front end of the processor, and the execution unit, which is the back end of the processor. So in the back end of the processor, we have units, execution units. These are essentially ALUs that we learned in our in order processor. And what they do is that they go through this table, they scan this table, and they pick the instructions that are ready. If we have many instructions that are ready, we can always feed the pipeline stage, the execution stage with the instructions. If there is not enough instructions that are ready, then your ALUs will be underutilized, of course. And then we also need some form of a forwarding mechanism to kind of tell these reservation stations that, look, this instruction, for example, I1 is finished, we update the reservation station, allowing the reservation station to update the instructions. Okay, so the kind of algorithm that we are going after is that the execution unit is going to scan through this and pick the instructions that are ready and feed them into the execution stage. Okay, um, and then execution stage looks something like this. So in our out of order execution, we're going to have this thing called functional units. And these functional units could be similar to each other's, could be different from each other's. I'm going to tell what they are. Yes, question. Yeah, so you can think about this as the same, essentially as multiples of ALUs. Remember, we said that superscalar, for example, you can just duplicate the ALUs, but you can also have different type of execution units. For example, there is no need for having a multiplier and a regular adder and duplicate all of them, because if your number of multiplication is much less frequent than the number of adders, you can save space and you can save complexity by having just an adder and having a multiplier, and then only schedule the multiplications into that execution unit. So this is what we have as the functional units. So the idea is that I have my fetch and decode units, right? And then I have my kind of reservation station here. And then I have a bunch of different what we call functional units, FUs. These functional units could vary. Could be, for example, as just regular ALUs, or it could be special units. For example, it could be a multiplier. Okay, so this would be, for example, a multiplier. This could be a divisor. This could be a floating point operation. And so on and so forth. So I can have variants of this. And what we need to do is making sure that instructions are assigned correctly to each one. So remember, I told you that in order to know whether or not something is ready to be scheduled, I said that the first thing that we need to do is making sure that the operands is ready. The second thing that we need to do is making sure that functional units are available. So for example, let's say I have three functional units. One is an adder, or so one is just a regular ALU, okay? One is a multiplier, and maybe one is a floating point operation, okay? So if the instructions that I want to run, two of them are ready, for example, this one and this one are ready, but both of them needs a multiplication, then I can, for example, just take this and assign it to the multiplier. But if the multiplier is busy, I cannot issue two of them. So that's where, like, how many functional units I have and how many issue processors I can issue at the same time is important. High-end processors have multiple multipliers, have fast and high-end ALU operations and so on. But if you want to save on the area, you want to save on power, then you reduce these numbers. But again, you want to balance this. So for example, if the majority of operations are ALU operations, you may want to have multiple ALUs and one single, for example, multipliers and so on. So the design of the functional units will be depends on sort of workloads and operations that you want to have, but typically you have a balance between the different types of functional units in your system, okay? Another important things that we usually do in order to simplify our design is that you can think about memory also as a functional unit, right? So instructions that use memory, they are talking to the quote unquote what we call a memory controller, which also can be considered as a functional unit. As a result, what we do is that we pipeline the functional unit itself. So for example, one functional unit might take only one cycle. The other functional unit might take many, many cycles, okay? As a result, one instruction essentially goes through fetch, decode, and execute, and is written to the ROB within, for example, 4 cycles. The other instructions might take like 10 cycles just in the execution unit. For example, if this is a memory operation, depending on how fast you can bring the data from the memory, this might take many, many cycles, okay? So different instructions might take different number of cycles in our design, right? All of them are pipeline, but usually takes different number of cycles in our design. And typically what we do is that although these are all, you can actually kind of like move it this way, we typically have what we call a bypass, allowing this to be written directly into the ROB and not wasting that many cycles doing nothing. So you don't want to kind of like let the instruction just continue in this doing nothing. Versus in our original pipeline stage, if you remember, our execution unit goes to the memory stage and doing nothing, which we were kind of like wasting a cycle. But now since we have this dynamic kind of scheduling, we can actually skip the memory if you want, okay? So our functional units essentially becomes a collection of different ALU operations, and your memory controller will also sits here. And you will have the pipelining of this. Some of them might take 1 cycle, some of them might take 2 cycles, some of them might take 10 cycles, and all of them will be written back to my ROB. And the ROB will somehow tell the future instructions that, okay, this is the next instruction, and move on. Yes. Yes. Yeah, the memory stage is essentially part of the executions. Yes. Yes. So one instruction might take many, many cycles. For example, floating point operations also usually not finish in 1 cycle. Multiplication usually doesn't finish in 1 cycle. And then once later we're going to talk about cache, you will see that depending on where your data is, if it's in like level 1 cache, it might take 1 cycle. If it's in level 2 cache, it might take 10 or 20 cycles. If in level 3 cache, it might take hundreds of cycles. So depending on that, one instructions might take a long time to be finished. Okay, so as I said, we usually have multiple functional units. For example, we can have just an integer add, integer multiplier, a floating point multiplier, or load store units, and so on and so forth. Okay, and the reservation station is essentially connected to your functional units. allowing you to pick any of these lanes. So if these lanes are available and the instruction, the operands are ready, so two conditions: availability of a functional unit and making sure that all the operands of that instruction is available, you then schedule it into your execution window. Okay? So this is kind of like what the updated version of the system look like. You fetch and decode, you do the renaming, you put things in your reservation station, you do the out of order execution, which could be multiple cycles within your functional units. And then you put things back into your ROB. And then once the instruction reaches to the top of the ROB, it will be retired and written back to the register files. Yes. Reservation station is for raw data hazard and for keeping track of availability of resources in the ALU. And later on, you're going to see that it's actually used to waking up the logic. So to kind of like know that whether something is updated is also updating the reservation station. Yes.
Instead of like explicit phase, that's all memory. And basically phase is called and like based on like whatever take one out.
Yeah.
Follow it to write
Yes. Yes. So yeah, the question was basically kind of overviewing the things. Yes. So instead of having a separate execution memory stage, now we are defining what we call functional units, which are equivalent to what we had as an ALU operation or a memory operation in our single cycle or pipeline. We're just combining it with multiple of them. And as I said, since this is a superscale and multiple issue processor, you can have multiple of the same unit. So you can have multiple adders, multiple multipliers, and so on and so forth, depending on how large and how fast your processor you want it to be. Okay? So this is kind of like how your reservation station would look like. Within the reservation station, each row is for one instruction. And within each instruction, you need to keep track of a bunch of things. This is just an example, but you can think about that your reservation station has these many columns. So usually you have a column that shows whether this instruction is valid or not, because your reservation station is a table. Instruction goes into the table. They may or may not be scheduled. Once you schedule them, you want to remove it from the reservation station, so you allow the next instruction to go into your reservation station. So this use is showing whether or not your reservation station is the current row in that reservation station is being used or not. The operand or operation is the opcode for that instruction. So basically telling you what sort of operation this instruction needs to have. Is it doing add? Is it doing a multiply? Is it a memory operation, and so on and so forth? The destination register is, the name is kind of obvious, is keeping track of what destination register is using. Source register 1, source register 2. Two important things that we need to have is source 1 ready and source 2 ready. This is where we keep track of readiness of the operands. 0 usually means that this operand is not ready. 1 means that this operand is ready. So in order for operands to be ready, both of these ready flags or ready bits needs to be 1. Immediate is that if this instruction needs to store some immediate value. FU is the functional unit that it needs to have. And ROB number is the row that belongs to this ROB. So for scheduling, the important thing is that when we are when we are actually putting things into the reservation station, at the same time, we also create a new row and entry for that instruction in the ROB. So reservation station, the steps in the scheduling is that reserving a row in the reservation station, and at the same time reserving a row in the ROB for that instruction. So these things happens at the same time. So if either of the reservation station or ROB is full, then that instruction will be stalled. So we cannot actually put it into the reservation station. So just keep that in mind that we always reserve a row in both reservation station and ROB. And the way that we link them is that we put the ROB line here. So for example, you say that, okay, line number 2 or row number 2 in the ROB is reserved for this instruction. You had a question. Uh-huh. Yes. So for example, for that add instruction, I put, for example, P3 here, P3 here, and says ready is 0. And then later when I1 is finished, then I need a mechanism to kind of go back and say that, okay, now it's 1. Yes. So the renaming happened before even putting things into the reservation station. So at this point, everything is physical registers. And by the way, this is just one way of doing this. Later on, I'm going to give you another way of doing this, which is a tag-based system. So you're going to learn about that as well. Yes. Are ROB and reservation station the same size? They can be. Typically, reservation station is a little bit bigger because there are some instructions that you want to kind of stays in the reservation station for longer time. But yeah, you can have the same size or slightly bigger. Why do you want to make space on both at the same time? Because so imagine that ROB is not available, right? And then you have an instruction here. And imagine that instruction goes to the execution stage. You need a space to store that value. And then if ROB doesn't have that storage, then the entire thing is messed up because where you want to store that. So we want to make sure that, oh, there is a temporary storage available for this instruction. Otherwise, I don't want to execute it. Yeah.
Size scheduler or the size of word, the ROB is where the temporary values that is retired.
Yes, the ROB is where you store the temporary values, and when you want to kind of like also restore the processor, and reservation station is the current state of each instruction for you to schedule it into the functional units. Yeah.
Like it sounds right though, but waiting and when that we get in out here constant.
Yeah. So reservation station, it's not in order anymore, right? So your rename write things, it just finds the first available row and write it to that. The execution station has this selection logic, which scans through the reservation stations and pick the whatever is ready. It doesn't no longer cares about the PC anymore, right? So that's where the out of order execution happens, right? All the criteria for executing an instruction is that the operands has to be ready. So these two guys needs to be 1. And then the functional unit that he needs to use is available. So this is the only thing that we care about. We no longer care about the ordering of things. Okay, I'm gonna give you a full examples of all of these all together, so you're gonna learn a little, you're gonna understand a little bit more. All right, so these will be the steps that we are using for an out of order execution. The namings and the number of steps is slightly changed from one design to another design. But generally, these are the steps that we have. So we have obviously our fetch states. The fetch states is the same as what we had before. If this is a superscalar multiple issue processor, you fetch multiple instructions at the same time. So for example, if this is a 4 issue or 8 issue processors, you don't fetch just one instruction, you fetch 4 instructions or 8 instructions. Other than that, your fetch is the same as before. This is also where you do your BTB and your branch prediction, and all of those good stuff also happens in the fetch. And we no longer have what we call a decode. So essentially, decode is usually a group of different things at the same time. I mean, in some terminology, we use the word decode. In some of them, we don't. But the new thing during the decode is what we call dispatch. Dispatch is when we know the opcode and the reservation we know the opcode and the source and destinations, and we put things into the reservation station. So this is when you actually write things into that reservation station table. And as I said, you also reserve an entry into the ROB. Here, an important thing is I said that copying values to the reservation station. This is not this case for all the different designs. So later on, you're going to see that in some cases, we just put the register number, but not the value itself. So there are two ways that we can dispatch. The one that I'm showing you here is that you copy the value into the reservation station as well, but you can also do it differently as well. As I said, if either of the reservation station or ROB is full, you need to stall the backend. So you no longer need to fetch new instructions because you're already full and you're kind of your sorry, it should be stall the front end. Your backend needs to kind of like execute the instructions. So you don't need to fetch new instructions. Okay, this has to be front end. Okay. Then we have what we call issue or yeah.
The reservation space is constantly updating because every time we actually execute instruction,
Yeah.
like
Yes, you have to. The reservation station is constantly being read and written to, and sometimes there are multiple ports to write into the reservation station, multiple ports to read from the reservation station. Yeah. Yes. Yes. The front end is fetch and decode and display and rename. Yeah. Yes, the value inside RS1. Remember that we have like P1 and P2. There are two things you can do in the reservation station, as you're going to see later. I can just say 1 or 2, this is the name of the register, and later on read the values. Or I can actually read the value of reservation station and put it into, read the value of the register and put the actual value in the reservation station. The examples that we're going to go show you is based on this. So we copy the values. We also now have a new stage called complete. This is when we copying the results to the ROB. We let the FUs to be available again during the complete. And what we also do is once we're writing it to the ROB, we also forward that value back into the reservation station. So so that RD is now once we write it to the ROB, we also forward that value into the reservation station and update the value of the RS1 or RS2 in that reservation station. Okay? And lastly, we have what we call a commit or retire. This is when we are taking the values within the ROB and write it to the register file and the PC and the memory. Okay? And another important thing is we also mark the old physical register as free. So if we put that back into the free pool as well, because we needed to use it for future instructions. So that's another thing that we do. Okay. Any questions so far? Yeah.
forward that value wherever.
Yeah, to the reservation station, to the source 1 or source 2 of a reservation station. You forward the value in the complete stage to that reservation station. Okay. It could be multiple of them, yes. So we're not going to go through the hardware implementation of this, but yeah, this might be actually a broadcast. So you can actually broadcast this value to everyone and say that, okay, whoever has X, like P3, here's your value. All of them will read that and update that. In your project, you're going to actually do it in C. People in the honors class are implementing this in RTL, so they actually do this in RTL. Yeah. Yes, that's one of the P's. You mark them as free and put it back into the free pool. No, it doesn't touch the value. It's just make it as available because later on it's going to be overwritten. All right. So I'm going to go through a big example. Okay. And in the homework, you're going to also see another example. And in the discussion sections, you're going to see another example of this. Hopefully, you'll see enough of an example so you can follow this along. This is, as I said, one way of doing this. In the computer assignments, we're going to slightly change this, and you're going to do it slightly different way of doing it. Just because there are multiple design decisions in order to implement an out of order execution. So let's actually go through. So what I'm showing you in this table, in this slide, is a busy slide. So here I'm showing you the ROB. So this is your ROB. This is your reservation station. This is a table usually called scoreboard, or just generally called, it's keeping track of the readiness of your functional units. In this particular example, I assume that I have 3 functional units, okay? The first functional units is general ALU. The second one is also ALU, but it can also do multiplication. And the third one is for doing memory operations, okay? And this Y or N means that whether they are ready or not. So think about it as zeros and ones, okay? This is my register alias table or RAT. If you remember, we had AREG and PMAP. I'm assuming similar examples that I showed you in the previous lecture, that I have 5 different architectural registers, and I have 10 different physical registers, okay? I also have this thing called free pool, okay? The free pool showing you what are the current registers that can be assigned. And lastly, I have the notion of readiness for my registers. Typically, this is either next to your register file or is a separate table that can be accessed. These are your 10 different physical registers. And at the moment, all of them are ready, which means that I can read them as I wish, okay? And this is the 4 instructions that I want to execute. Load and an add and an or and a load. And what I'm showing you on top of this slide is the cycle number. So cycle 0. And within each cycle, there might be multiple things happening. So you will see, for example, C1 has a fetch and it has a decode and so on and so forth. Okay? So with that, let's actually look what is happening in this step by step and cycle by cycle in this out of order processor. So the first thing obviously that happens for any instruction is that you have to fetch them. In this particular example, we assume that this is a 2-issue processor. So you fetch 2 instructions at the same time. For example, in this case, I will fetch these 2 instructions. The fetching is similar as before. PC needs to be equal to 100 in this case. You go to the instruction memory, you bring 4 bytes for first instruction and another 4 bytes, so total of 8 bytes to read that instruction. So that's your fetching, okay? So nothing special happens during your fetching. Then we go to the second cycle, and then we need to do 2 things. We need to first decode these 2 instructions that we fetch, and we also need to fetch 2 new instructions, okay? So I need to decode these 2 instructions. Decoding is also similar to what we had before. We have a controller. You feed these 2 instructions to that controller. You check the opcode. You check the RS1. You check the RS2. You do all of those things. If you need to also generate the immediates, you also generate the immediates. So all of those things that you learn in your pipelining happens there. Again, nothing very special happening here. You also do PC plus 8 in this case, and then you fetch the next 2 instructions in the second cycle as well. Okay, then we go to the third cycle, cycle 2. I started from C0. So you go to C2, and then there are 2 things that you need to do here. Now, those instructions that you have decoded needs to be renamed, and those instructions that you fetch, you need to decode. If I had more instructions here, of course, I would have a fetch as well. But just to make things simpler, I'm just showing you the example for 4 instructions. So just imagine that this will continue, right? So there will be fetching and decoding and so on and so forth. So what is going on during the renaming in cycle 2? If you remember, renaming was the process where we map the registers from architectural to the physical, right? So what we need to do is we take the sources. In this case, one source is x1, the other source is your offset, and you map them into a physical registers. How do you map them? You look at x1 and you look at your rat and see in your rat, let me actually use a different color, see in your rat what is the current mapping of x1. See that it's P1, so I put P1 here. 0 stays 0. You don't need to rename an immediate number. And the important thing is that for destination registers, you need to assign a new register. So you take x2. It used to be 2, right? So it used to be 2. You change that. You go to the free pool. You pick the first one. You put it here, right? So you put P6 here. And 2 is your old destination register. This will be actually written into this column in your ROB as well. So 6 and 2 here, and I use P6 here. But since this is a 2 issue, you actually do 2 renaming at the same time, right? So at the same time, you also do this. Typically, this happens, as I said, things happen in order. So you first rename this, then you rename this, okay? So now you look into the second instruction. You look into the second instruction. You look at x2 and x3. These are your sources. You have to look at the table and see what is the mapping of x2 and x3. In this particular case, you will see that x2 is actually P6 because essentially these two instructions are dependent to each other. So you put P6 here. x3 is P3. And then you also now need to map the previous mapping of x4 to a new mapping. The previous mapping was 4. Now you pick a new mapping. You go to the free pool, you put this here, and you move on. So you will have P7 here, and P4 will be your old destination register. So the new mapping will look like something like this. You will have P6, P3, and P7. So this will be your renaming logic at this point. What you can see is that basically what happens is that there are a few things that are being changed and updated in your tables. First of all, you remove P6 and P7 from your free pool. You can no longer assign them to any other registers. These things will later go back in the free pool when these instructions are retired. And then you also change the mapping of your rat, okay? So you change your mapping of your rats. Now you have a new mapping. You also need to remember your old mapping because this will needs to be freed. And then another important thing is that the reason that you need to remember your previous mapping is that if I want to flush this instruction, I need to also recover the previous mapping of that instruction. So if for any reason, for example, I need to flush this add instruction, I need to go back to the renaming table before this instruction. That's why I need to essentially say that, mapping from x4 is again P4 because that used to be what it was before this instruction. So that's very important to remember this old mapping as well. Any questions here? Yeah. You are confused about how remembering that mapping helps you with flush. So for example, before I renamed this instruction, this was the state of my rat, right? So if I, for example, tell you that I need to flush this processor at this point, okay? What should be the status of my table? It should be status of the tables when they were here, which is this, right? So I need to somehow remember this mapping that if I change things and now need to recover, I recover to the point that it was before. That's why I need to remember the previous map. If there are multiple instructions that you need to flush, you need to remember all of the mapping. So there are limited number of checkpoints. You can think about this as some form of a checkpoint, right? So usually processors have limited amount of speculation. They call it nested speculation. For example, you have an if then else and another if then else and another if then else. So like many processors can go up to 8 or even more. So you can have multiple of these checkpoints. Okay. You list of previous and previous of the previous and so on and so on. Yeah. Yeah, so the question is, where do you store this previous mapping? You can store it here in the ROB. You can also have it as a checkpoint for your RAT. So typically, most of the processors have multiple RATs. So the multiple tables, you kind of like have a checkpoints of that. Yeah. You don't need two places of storage, right? So you need one, only one. Yeah. No, right? So you don't want to release P2 and P4. You only release P2 and P4 when this instruction is retired. That's when, so the old destination register, which in this case is P2 and P4, will be released when these two instructions are retired. And the decode, you also need to decode the next two instructions. So these things happen in parallel, right? So similar to the pipelining, there is the overlap between stages. So as you're renaming the first two instructions, you're decoding the next instruction. And as I said, if this is a continuous stream of instructions, you also fetch the next instructions and so on. Yeah. Uh-huh. Uh-huh. Yes, we do the checking in the RS for the two instructions, so we don't need to worry about not renaming. So at this moment, you're just renaming things. You're not executing them. But later you will see that I can execute the first instruction, but obviously I cannot execute the second instruction at the same time. The second one needs to wait for load to finish. All right, so we go to the third cycle, fourth cycle, or C3. At this point, I need, after the rename, I need to do what I call dispatch. Dispatch means that I take the instruction that is renamed and write it to the reservation station. I also need to reserve a line in the ROB and write it to the ROB as well. And I need to then rename the other instruction. Again, here, if I had more instructions, there would have been a decode and a fetch as well, but I'm just simplifying the example. So let's see what happens in the dispatch. So remember that these two instructions are renamed, so they are ready to be written into this reservation station, okay? So the way that it works is that in the reservation station, I start from the top usually, but there could be other algorithms as well. I start from the top and find the first row that uses 0. It means that this is an empty line. So I take that line and put this instruction into the reservation station. So I make the use equal to 1. Then I put the opcode. In this case, the opcode is a 6-bit number. For simplicity, I just put load word, but it's in fact is actual like an opcode. Then I need to populate the rest of this table. So I look at the destination register and I put P6 here, okay? I look at the source register and put P1 here. I look at the second source register and put P0 here. And then, as I said, there might be an immediate. In this particular case, there is an immediate, so I put 0 here. And then another important thing is that as I put things here, I also reserve a line in the ROB. Same story with the ROB. I start from the top. I make the valid bit equal to 1. The valid bit is similar to the use bit. I put the P6 as the destination register into my ROB. And I look at this table and see that the old destination register is P2, so I put it there. I also put PC here because PC will help me to understand the order of the instructions. Remember, we need to keep track of the order. And then this column shows that whether or not this instruction is completed. In order to retire things, we need to wait for the instruction to be completed, okay? So now, so I put 0 here because this thing is linked with this one. And then there are a few other things that I need to take care of. I need to take care of source ready 2, and the functional units, okay? So the way it works is that for source ready 1 and source ready 2, I look at this table, I look at the register and see whether the ready table says yes or no. So I see P1, I see yes, so I put a yes here. The second one, since this is an immediate, right? It doesn't use the source register 2. So I put 0 here because 0 means P0 or X0 and it's always ready. So I put 0 here and put yes here. So this particular instruction only use one register. So I don't need to keep track of the other one. So I put yes and yes here. For the functional unit, I need to check the opcode, right? So this instruction is a load word instruction, can only be assigned to the third functional unit, okay? Functional units 0, 1, 2. So I can only put 2 here, okay? And ROB is already done. Last thing about this table is that when I put P6 in the destination register, I also make an important change here, and I make 6 not ready because now 6 is the destination register. The value of 6 is only valid when this instruction is completed. So I make P6 not ready at this point. Okay, so this is very important. So that would be for the first one. For the second one, same story. So I look at P6 and P3. I put P3 and P6 here. I look at this table, and this is where things are getting interesting. So P3 is yes, but as you can see, P6 is no, because essentially P6 is dependent to the previous instruction. This is where we're going to enforce that raw data hazard thing, right? So the raw data hazard will be enforced because this instruction has been scheduled first, and this instruction is dependent to this instruction, right? So you put a no here. This one doesn't have an immediate, so I don't put anything here. The FUs, usually, if I have multiple FUs that can be assigned for that instruction, I usually go round robin. So I do 0, then 1, then 0, then 1, 0, then 1. So usually I go round robin. So I put FU here, and I also reserve an ROB. So put a P7 here, P4 here, PC here, ROB1 here. Okay? So that would be all the steps required for dispatching an instruction. Any questions? Yeah. Yeah, you need to have a table for the readiness as well. So usually you put it next to the register file. Yeah, so think about it, your register file has 2 columns now. One column saying is it ready or not, and the second column is for the values. Yeah, it has to happen there. Any other questions? Yeah.
You say that immediate is only.
Yes. Yeah. So if it's an immediate, you usually put a 0 here as the other source register because you're not using that source register. You don't want to put any other number because those numbers could be dependent on other instructions, and then you're depending for no reason, right? So you put 0 all the time. Yeah. So is it like, do I need to read 0 or yeah, like, do I need to read the immediate or do I need to read the source register? Yeah, so you can actually have it. You can also have like a multiplexer kind of thing, right? You can have a multiplexer that takes the immediate and source register too, similar way that we had it before. So to choose between the two. All right, let me also do the renaming for this, and then I'll give you some time to take a break. So another steps that needs to happen during C3 is the renaming, and renaming needs to happen for these two guys. So this is the updated version of your reservation station and your ROB, and this is the updated version of your readiness table and your FUs. So in order to rename, same story as before. I look at X5 and X4, X5 and X4, and I see that the previous mapping was X4 was 7 and X5 was 5. So I put P7 and P5 here. And now I need to also rename X5 So I look at the free table, free pool, I see P8 here. So I put P8 here. So 5 becomes 8, and I put 8 here, and I remove 8 from the free table as well. Same story for load word. X0 is P0. I don't need to essentially rename, so I can like assume that P0 is always 0 as well. So X0, P0, 0, 0, and then I need to rename 4 again. So 4 used to be 7, now it becomes 9, and now the old one becomes 4. Okay, so I'll pick this up. I'll put this here, and I put P9 here, and I remove P9 from the free pool as well. Okay, so this would be what happens in C3. We go to C4. Let's have a quick break. We're gonna talk about C4. Okay. All right, continuing on. Can we do it at the end? Thank you. Okay. Okay. So we go to the next cycle, and in the next cycle, I need to do now what we call an issue. So issue essentially happens at every cycle. So all of these things happen at every cycle. It's not like it happens only in certain cycles and doesn't happen in certain cycles. The reason that I'm showing you here is because now I have something to do. So for example, in cycle 3, we also search for an instruction to be issued. But keep in mind that things cannot be happen at the same time. So you cannot dispatch an instruction and issue it in the same cycle. Issue happens in the next cycle. Why? Because these are registers, okay? So these are registers, and similar to the registers, you cannot like write to the registers and read, and then use that value in the same cycle. Write happens by the clock, okay? So when I dispatch things, I can issue them in the following cycle. So in cycle 4, essentially what we call the issue logic, scan through this reservation station table and try to pick as many as instruction as possible and issue them into the functional units. How many instructions can be issued in the functional unit? There are two things that you need to consider. So one is some of the processors have some cap on the number of things that they can issue. The name's a little bit confusing. So when you say 2 issue, you might like wonder that is this 2 issue, like this is maximum 2 issue or not. So you can actually fetch 2, but issue 3 sometimes. So depending on the design of the processor, this could be different. But of course, the maximum that you can issue is the number of functional units that you have. So you are definitely capped by the number of functional units, but the number of things that you can issue depends on the processor itself. In this case, we can assume that they can issue 3 at the same time, or sometimes they can issue 2 at the same time. Again, that depends on the definitions and the assumptions about the processor. But in either case, there is some maximum number of things that I can issue. The issue logic tries to maximize that, because if I can maximize that, I can improve the performance. So how do I make a decision of what can be issued? I go through the table, let's say 1 by 1, and I look at whether or not my sources are ready and which functional unit is going to use. So I see that, okay, source 1 is ready, source 2 is ready, and it's going to use functional unit 2. I go to my functional unit 2 and see if that's also ready. If these 3 things are all ready, then I'm going to issue that instruction. So I'm going to issue this instruction. I'll go to the next one. I see that source 1 is ready, source 2 is not ready. So that means that I cannot issue this instruction. So I move on. I go to the next one. I see that the use bit is 0. So there's nothing there. I cannot issue this one. I check this one, same story. So I only thing that I can issue is this guy, okay? When I'm issuing the instructions, there are 2 things that is happening. I usually remove it from the reservation station because I no longer need to keep track of it. The second thing I do is I make this functional unit to not ready, because this instruction now goes into the pipe to that functional unit. So that functional unit cannot be used again until this instruction is completed. Okay, so I move this to no, I remove this from the table, and I move on. Okay, so make this no, remove it from the table, make the use bit 0, and I move on to the next part of the design. So that's your issue logic, happens every cycle. Okay, now I also need to dispatch the more instructions into my reservation station. In this case, I also need to dispatch these two guys. Okay, so how does the dispatching works? Dispatching, I need to put things in the reservation station and I need to put things in the ROB. So I looked at the first instruction. Okay, I see P7 and P5. I put P7 and P5 here. I put the use bit equal to 1. I put the opcode of OR here. I put P8 here. Once I put P8 here, I also need to immediately make the ready bits of P8 to no, because now this is a destination register. Oops. I also need to look into my readiness of P5 and P7. I look at the table, I see P5 is ready, P7 is not ready. So I put yes here and I put a no here. I don't have an immediate. Which functional unit should I use? As I said, you usually go round robin. So since this was 0, this is going to be 1. I also reserve a line in my ROB, P8 here, P5 here, 108 here, and 2 here. Okay, so that's for this guy. For the other instructions, same story. Use bit 1, load word, P9 here. I put no here. I look at the other two, P0, always yes. This one is also P0 or 0. I put yes here. Immediate is 0. Functional unit has to be 2 because this is a memory. ROB 3. I put here, 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 and here. Okay? Yeah. Say it again. Dispatch happens of like how many we can dispatch. So for example, in this case, we can dispatch 2 instructions, so it happens at the same time. Yeah. Mm-hmm. Yeah. Uh-huh. You don't need to clear up the rest of it, right? So all you need to do is like use bit is equal to 0. Okay, so that's all we need to do in C4. And again, I repeat this multiple times, but here you also have a bunch of other things. You have your rename, you have your decode, you have your fetch. So many things can happen at the same time. Okay. All right. So now we go to C5. And C5, again, all of those things happen, but the new thing that happens is that instructions can get completed, right? So remember that we issued that load instruction here, and it went to the pipeline. Depending on how many cycles it takes to finish an instruction, instructions can complete in varying times. So for example, most instructions finish within 1 cycle. So like a regular add or and all those things typically finish in 1 cycle. But there are other instructions that might take multiple cycles. So it's not like I issue in this cycle and then the next cycle I should expect it to be completed, but some instructions are, okay? So for example, let's assume that this load word happens to be completed within 1 cycle. Let's say it's a hit in L1 cache. So it's going to be completed. What will happen with complete is that we actually update our ROB. So the functional units write things to the ROB. So it says that it's completed. So it writes a yes or a 1 in the complete table. But the more important thing is that we also makes 2 things ready. So we first makes the functional unit ready again because this instruction is no longer in the functional unit. And another very important thing is that P6, okay, should now be ready. Okay, so P6 is P6. We're gonna mark it as ready here. And then since this is ready, we're also gonna mark this as ready here, okay? So we're gonna mark P6 ready in these two places, and then we're gonna also make the functional unit ready in the same cycle. Okay, so that would be the story of the complete, and I cannot complete and retire within the same cycle. So there needs to be one more cycle for things to be retired. Okay. Any question here? All right. So now, so there's nothing else to be completed. There's, as I said, also we always in every cycle we search for instructions that can be issued. So in this particular case, we look at the table and see which instructions can be issued. Okay, look at the first one. This is 0, so I cannot do it. Look at the second one, and as you can see, I have P6 just becoming ready. Okay, so here again, different implementation might have different ways of doing this. Here we assume that if things are completed within the same cycle, they can be, the future instructions, the dependent instructions can be woken up and be fed into the pipeline. Depending on the depth of the pipeline, this might vary. So there are some instructions that takes a 1 cycle or even 2 cycles to become to be woken up. There are actually what we call speculative waking up, that once we issue, we also wake up the dependent ones. In this case, you can assume that once the instruction is completed, I can wake up the dependent instructions within the same cycle. So in this case, I can wake up this add instruction since now this has been written to 1. Okay, so what was the procedure for issuing? We make the functional unit to not ready. So this would be no. We remove this from the reservation station and we go to the next one. Okay, so we remove this and we make this no. But as I said, we typically try to issue as many as possible based on the availability of our functional units. So we go to the next one. See that this is yes, but this is still no, so I cannot issue this one. But then I go to the next one, see this is yes, this is yes. It used functional unit 2, and I check functional unit 2 and see that this is also yes. And again, I can issue, like once it's completed, I can issue the next one within the same cycle. So I also issue this guy into the issue queue. I make this as no as well. So this would be how my reservation station looks like by these instructions here. Make sense? Perfect. Then we go to the next cycle. Now the new thing that can happen is that I can retire instructions. Yes. In this table here? Like a column here with the function. Yeah, you can. I mean, I'm just showing you here this to kind of make things simpler to track. But yeah, of course you can put it there. The only problem is if I have multiple instances of the same thing, then I need to have stored them, like update them all, right? So that's another thing. So the good thing about centralized approach is that you just store it one place and everybody read it from there. If you distribute them, you can actually read it from multiple places. All right, so in C6, you can retire instruction. What is the criteria for retiring? It has to be completed and it has to be top of the ROB. In this case, since the ROB starts from here, all we need to do is essentially writing this back to our register file. And the important thing is that we have to free the old register. If you look into here, the old register was P2. So I put P2 back into my free pool at this point. Okay. And then the actual value of the registers in the register files are also updated. I'm not showing the values here, so you don't see that action to be happening, but that's also another thing that is happening. Okay. So that's it with the retire. Also, some instructions will be completed. Remember that in the previous cycle, I fed 2 instructions into the pipeline, right? So I technically can have 2 instructions to be completed. To make things interesting, let's assume that the second load board might take 2 cycles to finish. This is just an assumption that I'm making. So as a result, let's say that only this add instruction is completed in this cycle, and the load takes another additional cycles to be completed. So what will happen is that I make yes here. I release this one, but I don't release this one. Since P7 is ready now, I put P7 ready, and I also update my reservation station with P7 ready. So that would be the complete stage here. Then as I said, I also again scan and I see now this one ready. FU is one. FU is one was ready, so I can actually issue this instruction as well, and I turn this into no, and then I continue to the next cycle, to the cycle 7. In cycle 7, I retire this instruction because this is also top of the ROB. I can retire this instruction. I put P4 back into the free pool, and I increment my ROB, top of the ROB or head of the ROB one down. And then since I issued this instruction from the reservation session, this has been already removed. And that's the only one I can retire in this cycle because this other one is not completed yet. And then within the same cycle, there's also things that will be completed or instructions will be completed. As I said, we assume that this second load takes 2 cycles to be completed. So this one is also completed. So this one becomes yes. This one becomes yes. These 2 will be released. P8 and P9 going to be ready. Okay. And that's all we need to do in this cycle. There's nothing else to be done. And then we go to C8 and then we retire. Again, the number of instructions that we can retire depends on the design of the processor. Usually the same number that we can fetch, the same number we can retire. So in this case, I can retire this guy. Since this one is also ready, I can retire this one. So I retire both of them. And what I do is that I put P5 and P7 back into the free pool. Okay. So at C9, the head of the ROB is here. My tables are all empty. Everything is ready. Everything is ready here as well. And my free pool is, the current mapping looks like this, and my free pool looks like this. Okay. And as I said, this is an ongoing thing, right? So like new instructions comes in. So you never like, you're not free of anything. I'm just showing you a snapshot of the pipeline of the entire design for this 4 instructions. But it's just a dynamic thing. It's keep going. Yes. Yes, so you put you free the old destination register once that instruction is retired. Say again. So the question was at the retirement, the old destination register goes back to the free pool. Yes. So as you can see here, this instruction is going to be retired, right? This instruction going to be retired. The old destination register is P5. So I'm going to put P5 here. So I put P5 in the free pool. Okay. Any other question? Yeah. So the branches in this going to be so at some point the branches basically goes into the same table similarly. It's going to be issued into the execution unit and all that. And then at some point you're going to realize that you made a mistake, so you need to recover. But as I said, typically we have branch predictors and we move the branch resolving logic into the fetch and decode. So usually the branches is not going to end up in this table, but they can. They can, and then you just execute them regularly. But typically for these high-end processors, the branch is resolved during the decode. You don't even like get into this point. Would be a misprediction, and then you need to recover. So there will be a recovery logic and so on. Okay, so these are the main 3 things that we wanted for auto order. So now you know all the important ingredients of an auto order. Hopefully you will redo this example for yourself. And as I said, in your homework and in your discussion sessions, we're going to go through 2 other examples. So you kind of like, you understand it. And typically, in your homeworks and quizzes, we kind of ask you some portion of this. Sometimes like tables are pre-filled. Sometimes we want you to fill the tables. And then in your CA3, you're going to implement something similar to this. It's going to be a slightly different version of this, but it's going to be the same, vein of like designing an out of order and so on and so forth. Okay? So this is kind of like the updated version of your design. You have your RAD, your physical tables, your FUs, your ROBs, and this essentially becomes kind of your reservation station here. Okay. Any final question about this? Awesome. So for the rest of the lecture today and a little bit of next week, we're going to talk about the challenges and different design trade-offs. For our order, there's actually quite a bit of a different things that you can do. There are different thought process, different ways of implementing things. So it's not like just one way of implementing things. Okay? So just a quick recap. We need dispatching and renaming. We need retiring and reorder buffer. We need a scheduling and reservation station. And we need functional units to fire and complete. And fire and issue is the same thing. So some people call it fire. Some people call it issue. Just keep in mind that these are the same thing. Okay. So the 4 things that I want to talk about is different design choices and what are the trade-offs, the mechanism for recovery when there is a misspeculation like branch misprediction, then different methods of forwarding, and then if there are any other new issues or results as a result of out of order execution. Okay, so there are 2 ways that you can design this out of order execution. The first one is the one that we showed you. That is, you can have a separate reservation station and a separate ROB. Okay, but this is usually what we call a distributed ROB, distributed a reservation station. But since these are very interlocked to each other and quite integrated, I can actually have what we call a centralized design, but RS and ROB is the same thing. Okay, so essentially all I need to do is that if I add more columns here, then this table becomes both my reservation station and my ROB. This is usually what we call an ROB-centric design. That essentially my reservation station, my scheduling queue is also the ROB itself, because there's nothing fundamentally different between them. What do you think are the pros and cons of this approach? Anyone wants to comment? Which one is better? Which one do you think is a better option? Yeah. If you have it combined, the designs would be more simple, right? So you have less kind of back and forth between the ROB, less wiring. So that would be one way. What is the disadvantage of this approach? Yeah.
The update actually takes more computations.
The update takes more computation power. Why? Yeah, so you do more things on the table in general, which means that then your kind of table becomes a bottleneck, or there will be lots of ports going in and out. So there will be like design challenges when you're designing a centralized ROB, because you need to schedule things, issue things, complete things, retire things. All of them happens in this table. So in terms of like power management, temperature management, this becomes really, really hot because there's lots of switching happening at the same time. So you want to distribute this a little bit to kind of reduce that, but there are actually both of them are being extensively used in modern processors. So you can have the centralized model where the RS and ROB are combined, This is great for simplifying because everything is shared. But the problem will be that the power consumption and the area designs would be very challenging. Okay, so that's one trade-off to just keep in mind. If you actually look into many different designs of modern processors, you will see some of them are centralized, some of them are distributed. Okay. Another thing that you will see is that we show you that we have one big reservation station, okay, and bunch of functional units, right? So for example, in this case, we had something like this, right? One centralized RS, bunch of different functional units. The other option to this would have been that I have for each functional unit, I have a separate reservation station. So I make the reservation stations further distributed, that each functional unit, since I already decide which functional unit I'm going to use in the reservation station, right? So I can just assign it to that reservation station and make the others not bother. So what is the pros and cons of this approach? Which one do you think is better, or what are the advantages and disadvantages of this approach? Yeah. Oh. Okay, so searching is simpler on the blue one, right? So searching instructions is significantly faster and easier on the blue one versus the red one or orange one, whatever you call it. Uh-huh. Anybody else wants to comment? Yeah. It might be a little bit, yes. So for the decentralized one, a little bit extra circuitry for searching and all would be. So here on this one, you'd reuse some of that, but for this one, you have extra things. Oops, sorry. You have extra things that is like needs to be added here and here and here, right? Yeah. Yes, so the biggest problem and biggest difference between these two is the utilization, right? This one has poor utilization because if you happen to have like a sequence of a lot of ads, for example, this first one quickly fills up, but there might be space here and here, but you cannot assign it to them because this might not be functional units for that. Versus here, you can utilize the entire functional unit easily, right? So the utilization of this one is not great versus utilization of this one is much better. Yeah. Yeah. In order to maximize the utilization, the left one, you can have many functional units. On the right one, you cannot have many functional units, right? You need to kind of combine them into some groups. Yeah. Okay. So yeah, these are actually all the good things. I mean, to summarize, I would say the two main thing is that the red one, searching is more time consuming and more complex. And it also has the same issue as the centralized ROB and RS, where all the things happens in the same table. So power consumption wise, area wise, temperature wise, the left one, there's more stress on the same area versus the right one, things are nicely spread out. So you can actually physically, move them around. But the nice thing about the red one is that utilization is much nicer. So if you have a sequence of all loads or all multiplications, left one can handle it much better than the right one, right? So these are the trade-offs that you're seeing on the centralized approach versus the per execution approach. Okay. Another trade-off that we are seeing, and by the way, all of these things, as I said, different modern processors use them differently. There is no like a one right answer. There is usually like a combination of them. So you see some processors using the centralized approach, some of them using the per execution approach. Okay. Another thing that we need to think about is, this is actually what I asked and what I pointed out when I was talking about the design was, when is the right time to read the data? And here are the two options that you have. There is one thing called read before issue. Okay, this is also called data capture. And this is the idea here is that when we are putting things into the reservation station, we not only put the name of the register like P1, but also we read the value and put the value with it. So we store the value when we are dispatching the instruction. We read it from the register file, put it into the reservation station. Okay, this is called read before issue, because before issuing this instruction, when we are dispatching this instruction, we already read the register file. Okay, the other option is, I don't put this value in my reservation station. I just put the name. When I'm issuing this instruction, okay, right before putting it into the functional unit, I actually read it from the register file. So I actually spend one cycle reading it from the register file and then putting into the functional units. Okay, this is usually called read after issue or non-data capture. So what do you think are the difference between, what are the pros and cons of these two approaches? Yeah. For read before issue, you don't need to spend that one cycle. Performance kind of would be similar in both cases, because essentially you still need to read things. It's just a matter of when you're reading it. So for read after issue, your dispatching is faster, right? You just put the name of the registers and you're done. But your actual issue is slower. For read before issue, your dispatch is slower, but your execution is faster. So it kind of, in terms of performance, is pretty similar. Yeah. Yes, you save some storage inside your reservation station, right? Because if I want to actually store the values, I need to have a column here to store the value. Versus if I do read after issue, you store less values, right? What about forwarding? Which one is easier for forwarding?
I guess it's not very issue because once you like need the data, it's easier for you because like maybe my data is finished fast.
I mean, in terms of, again, timeline would be the same, because you either need to update your kind of register file or you need to update your reservation station, right? So in terms of timeline would be the same, but in terms of where you read that data, it's slightly different. Because if I want to update something, if it's a centralized register file, the only thing I need to do is just updating one value, and everybody is reading from that value. But for the reservation station one, I need to update a bunch of things at the same time, right? So that would be the challenge. So what is the disadvantage of? So there are two good things that we learn now. Well, what is the disadvantage of read after issue? The disadvantage is similar to the one that we have for reservation station, that now you put all the stress to the register file. So everything, all the write backs, all the retirement, completion, and issue, all has to go through the register file. So again, the number of pins that needs to go in and out for your register file would be huge. So there will be still a lot of activities going on in the register file, versus if you actually move some of it to your reservation station, you kind of distribute this a little bit better. So that would be the kind of like the major bottleneck and the major problem with read after issue. Okay. Another important thing is that the reason that this is important, that it actually changes to some extent the way that we are doing the renaming. Later we're gonna explain. So the one that we so far did was using the physical registers and putting the physical registers. Later, I'm going to explain what is called Tomaso algorithm. And there you're going to see that instead of like actually having a RAD table and putting the physical registers, we're going to have a tag system. And we're going to basically kind of like use this tag system to keep track of the registers. Okay. So yeah, this is the kind of the difference between them. So we can use a RAG and a physical register. This is what we discussed so far. But then you can also have like a mechanism for tag systems and broadcast those tags and only use the architectural registers all the way together. So we will have a combination of architectural registers and tags. And you can think about tags as kind of like equivalent of your physical registers, but they're not exactly physical registers. This is actually the ones that you probably going to implement in your CH3. So we're going to talk a little bit about this later to give you a little bit idea of how does this done. Both of them are both valid, decisions, and as I said, widely used in modern processors. This is kind of like the picture of the difference between the two. So I have a fetch, and I have usually a pipeline register, some form of a buffer. I have my decode and rename. I have my ROB, okay, and this one is I just decode and puts the instructions and their tags, and I only read them when we want to issue them, okay. This one though is that I keep track of values inside my issue window here, so I already read them from the register file and then issue them, okay. So this one is what we call the read after issue, okay? And this is what we call the read before issue, right? And as you can see, the difference here is your reservation stations becomes much smaller, but then you put the physical register file in the path of execution, versus here you keep track of data, and then you read things off of the ROB and reservation station, and your register file only needs to update the reservation station, and your functional unit essentially just write back to the reservation station, versus here your functional unit write back to the register file. So that's the difference between the two options, okay? This is also usually called explicit renaming, because we explicitly rename x1, x2 to p1, p2, p3. This is again what we discussed in the class. This one is implicit because you essentially keeping x1, x2, x3 in your reservation station, but in fact you're using the tag system to kind of rename. So you still do the renaming, but the renaming is slightly more implicit compared to the explicit renaming that we do on the left side. Yes. Yeah, because so the question is why we don't store the data here, but we store the data here, because here everything is written back to the register file. Okay, so the ROB is only keeping track of the instruction and their corresponding tags. If I want to update anything, if I want to recover anything, all happens in the register file. So register file, think about it as a kind of bank of registers that like have checkpoints and all that here. But here, I want to basically read one time from the register and put it in my ROB and my reservation station and be done with it. Everything else, if I need to update anything, I update it in my ROB and I update it in my reservation station. So the checkpointing and everything relevant to that happens in the reservation station and happens in the ROB. The write backs, as you can see, happens in this case, happens to the reservation station and happens to the ROB. So ROB needs to know that this is completed. So it write backs the actual data. So as you can see, once it wants to commit, it takes this data and writes it to the register file, right? So this is kind of like, this way you know that the value is there and you move forward. Versus this one, you no longer need to do anything. When you're committing, you're only telling the register file that this value has been updated. That's all you need to tell to the register file. because register file already has the value. It just means that, oh, this instruction has been committed. That's it.
So, of course, it's already right.
You do forward, right? So essentially forwarding here means that the functional units needs to update the functional register, the physical register file. But just keep in mind that since this might be speculative, you have multiple instances of the physical register file. So you kind of need to have multiple checkpoints of the physical register file here. So that's why you kind of do the forwarding. So you have some form of a buffer within your register file to keep track of things, because you need to be able to recover, right? So when I'm showing you a physical register file, think about this as multiple instances of the physical register file that kind of like update each other. Yeah. So usually what we call a dirty and a clean. So we will have a dirty one, which you write things to it, and you have a clean one, which is kind of the last checkpoint. And when you're committing from rewriting from the dirty one to the clean one. Yeah. Your physical register file becomes a permanent storage, but as I said, you have multiple copies of that within the register file. Because if you need to recover, you want to recover from the last known checkpoint. So this would be when you wake things up. Okay, so when you have your register file and you do read before issue, so you have your register file, you have your issue or reservation station, you have your functional unit. The forwarding happens here, and the waking up also happens here, right? So you forward the data to your reservation station. You also check the next instructions that are dependent and update that. And then the register updates happens only when you have the instruction being retired, right? So when you're retiring, you update your register file. In the case of non-data capture, you have your instruction kind of sitting here, but the values are actually being read from the register file. So in order to wake up, you wake up the issue, the reservation station. But if you want to forward, you forward to your register file. Okay, so you forward to your register file, but you wake up from your issue queue. In this other case, you both forward to your issue queue and wake up from the issue queue. So you do both at the same time there. Yeah. Wake up means you have an instruction that is dependent on the previous instruction. This instruction is finished, so you can actually let this one go. So you need to wake it up. Okay, I'm gonna pause here, and then we're gonna next week we're gonna continue this conversation. All right.